Okay, so we'll start now. Welcome to the session on virtual labs. So yesterday in the previous session, we have seen some of the experiments, very basic experiments. That is verification of gates on virtual lab. So we are using the portal of IIT Roorkee. The link I have already shared it with you people, right? So you have different experiments over here. So we'll just start with the few experiments. We'll try to cover 2 or 3 experiments. So yesterday we have seen half subtractor, right? So today let us go with the full subtractor. The theory part, you people already know it. First we write the truth table. From that truth table we just draw the K-map, and then from that K-map we just group the elements and form the min terms to form the total equation for difference and borrow. And after that equation, we just try to connect the ICs in proper fashion so that we get the expected output, right? So these ICs can be used on digital trainer kit, that is on hardware, and connections we have to do in similar fashion, right? But as I said, we are now into the virtual labs. So virtually we'll be working on all these experiments. So this is the main power switch. And before we go with the experiments, we have to turn on the power switch, right? Now the connection is already there, right? We can just check the functionality of the circuit. So here we have the 3 inputs for the full subtractor, A, B, and B in, right? Okay, so here we can change the inputs, and as we change the inputs, we'll be getting the respective outputs, right? So let us go with 1 minus 0 minus 0. 1 minus 0, it will be 1, and the borrow will be 0, right? Let us check for 1 minus 1. When we make it 1 and 1 for A and B, we'll get difference and borrow as 0, 0, right? And we, as I had said you, we can add it in the truth table. So 1 minus 1 minus 0, we are seeing the result here in the truth table. Then you can change the input, all 3 are ones. The same you can print it in the truth table, right? So you can go with the different combinations. That is 1 minus 0 minus 1. That is 1 minus 0 will be 1, and 1 minus 1 will be 0, 0, right? So 0, okay. 0, 0, 1. 0 minus 0, it is 0, and that 0 minus 1 will get both the outputs as 1, right? Same thing, whatever is being seen through the LEDs, that same thing is being reflected in the truth table. 0 minus 1 will be 1, 1, and that minus 0, it remains as it is, right? So all the combinations you can just verify using the virtual labs. Let us go with some different comparator. Let us take comparator. So what is comparator basically? Did you people learn it in theory? Comparator? Am I audible?
Yes, sir.
Yes, sir.
Yeah. What is comparator? Can anyone say what is comparator? Did you people learn it in the theory? Yes. Yes or no? If no, I'll just try to summarize it. If yes, then I'll skip that part. One of you, please reply.
Summarized.
Yeah. But did you learn it in the theory or no?
Yes, sir.
Okay.
Yes,
Yes, sir.
sir.
Okay. Okay. So comparator, basically we can say that there are in terms of analog and digital, if we just look into it, right, there are analog comparators also and there are digital comparators also. So what I am drawing now, you have seen this symbol earlier. What is this symbol? This is analog comparator. What is this symbol telling you about? I'm giving the clues now.
Op amp.
Yes, exactly.
Okay.
So op-amp can be used as comparator for analog signals, right? So let me quickly brief about it, how it can be used as a comparator, right? So what I'm doing, the inverting terminal, this is the inverting terminal, that I'm giving it to a sine wave, right? An analog signal. And non-inverting input, I'm just grounding it. Means it is always at voltage 0, right? It is always at voltage 0. That is grounded, right? So now what this comparator does is, the main thing which we have to see before the working is it doesn't have any feedback. What do you mean by feedback? Feedback is output connected back to the input, right? So here we are not using any feedback. So what output we may expect here is either it will be near to plus VCC or minus VE. Okay, output of this op amp, it will be near to plus VCC or minus VE. It will not be any other output. Why it is so? Because gain of this op amp, it is very large. So I think in first year you people have studied characteristics of op amp. So one important characteristics of op amp is gain of the op amp is infinity. That is ideally, right? I think you have studied Zin. Input impedance of op amp is infinity. Then output impedance of op amp is 0. Then bandwidth of op amp is infinity. Slew rate is some value, right? Slew rate is 0, right? Yes or no? You people have studied it. So what is the ideal gain of the op amp? It is infinity. Means what? If you give any voltage at the input, your output should be infinity. I'm just going out of syllabus. Okay, it is not there in the syllabus, but the people should know it. What is gain formula? Voltage gain. What is voltage gain formula? What is voltage gain formula?
Output
It is
voltage divided by input voltage.
correct. Very good. Output voltage divided by input voltage. Correct. Now, can you write the formula for V naught from this equation? It will be gain into input voltage. I'm just shifting this VI over left hand side. Right. Now this is the formula for output voltage. Now what did we say? We are saying that the AV is infinity. That is ideally. Okay. Ideally gain is infinity for op amp. But ideal case doesn't exist. In the world, there are no ideal things. No ideal diode, no ideal op amp. Right? But if we think practically, yes, the gain will be around in the range of 10 raised to 6. Okay, more than 1 lakh. It will be around 1 lakh or it will be more than 1 lakh. Means what? Say, let me take 1 lakh only. Okay, 1 lakh. I'll write 1 L, L for lakh, into, say, if you give 1 millivolts as input, right? If you are giving 1 millivolts as input, very, very interesting thing I'm telling you. Okay, the input voltage I'm giving is 1 millivolt, right? And that 1 millivolt, you just multiply here, 1 milli. So what output you are expecting here? Say 1 lakh means it is 10 raised to plus 6 into what is 1 milli? 10 raised to minus 3. So what output you are expecting here? Yes or no?
Yes, sir.
1 kilovolts means what? It is
10 to the power 2.
10 to the power 3 kilo. 10 to the power 3, that is 1000 volts. Correct? Now
Yes,
my
sir.
question is, will you get 1000 volts here? Will you get 1000 volts at this point? Question is, will you get 1000 volts at the output of the op-amp practically?
No, sir.
No. Why no? I'm just giving you the clues. Why no? Op-amp, not only op-amp, any device, any electronic device, it can give the output. It can give the output up to VCC. Actually, practically, it will not be even up to VCC also. Say VCC is 12 volts. Okay, or say 15 volts. 12 volts or 15 volts, right? Then your op-amp cannot give the output voltage greater than 12 volts. In fact, it gives 1 volt lesser. Getting? So, what I'm trying to say, why did I tell all these things for you? What is the expected output? Expected output is 1000, correct? So if I want to draw 1000, right, say for 1000 to take the range, so say this is 1000, okay, this is 1000 as per the scale. If this is 1000, this will be 500, correct? Getting?
Yes.
Yes, sir.
Then let me divide it again. 100, 200, 300, 400, 500. So this is 100, right? And within this 100, you just divide up to 10. So 1, 2, 3, 4, not able to draw correctly. 10 parts again. So each part will give us 10 volts. Correct. The first part, you can think that first part is 0 to 10 volts, right? So now I'll try to draw what our expected output is. So our expected output is something like this. Correct. Correct. Up to plus 1000 and up to minus 1000. So this is our expected output as per this formula, as per this concept, right? This is our expected output. But where the output is restricted, it is restricted by what? It is restricted by this plus VCC and minus VEE. Getting? So output can be up to 11 volts. Maximum output can be up to 11 volts. But now here we should get 1000 and minus 1000, right? But it is restricted to, or you can say it is being cut. It is being cut at these 2 points. That is plus 11 volts and minus 11 volts. Getting?
Yes, sir.
Now, if you zoom into this part, actually this was our expected output, but it is being restricted or being cut at these 2 points. So if you zoom in, then your zoomed output will look like something like this. It will look like this. It will not look sine wave. Why? Because it is being restricted. It is being saturated. I think you people have learned about, heard about this word saturated. Saturated means
Yes.
what? The maximum value which the op amp can give, it is 11 volts and minus 11 volts because of power supply. So what I am getting here, I am getting square wave. Correct? Why I am getting square wave? Because the output is restricted. We cannot get sine wave. If you would have got 1000 volts, then you would have got complete sine wave. But that sine, it is being restricted or it is being cut at these 2 points. So we will get square wave. Right? Now, what I was trying to say, when you are giving sine wave as input, what output we are getting? Square wave from this circuit. Right? From this circuit, if you are giving sine wave, we are getting square wave. Right? So we were speaking about comparator. Correct? We were speaking about the comparator. So what is happening here? This is all about analog comparator. Okay. This is all about analog comparator. Don't think that these things or these concepts are not useful for us. Actually, these are very basic things and frequently used in companies' interviews. Right? Whenever you will be facing any interview from the core company, these questions will be asked. So these things are very fundamental things. Okay. So let me proceed. So what is the input? Input is the sine wave. What is output? Output is square wave. Correct. Now this circuit, it will compare the things. What it is comparing? It is comparing this signal, the signal which is coming at inverting point, inverting input. It is comparing that signal with this signal. What is this signal? It is 0 volts. Right. So comparator, what it does, it compares the two things, this signal with this signal. Right. So how it will compare? It will compare. How it will compare? See, say for example, if the sine wave it is going up, that is if it is greater than 0. When it is moving up, right, it is greater than 0. So when the sine wave it is moving upwards and it is greater than 0, that means this input is greater than the second input. Correct. So when this input is greater than the second input, right, the op amp will give the output square wave. It doesn't has any other output. Either it will be plus Vsat or positive saturation, or it will be minus Vsat, that is negative saturation. No other outputs it can give. But the input is given to inverting terminal. Correct. And that inverting terminal is greater than non-inverting terminal. So it will invert the output. So as the input will go in positive half, output will be square wave in the negative half. Are you getting?
Yes.
Now what will happen if the other thing will happen? See, if the input is below 0, the other part, right? If this is 0, if the input is becoming below 0, then which part is greater than the other? The non-inverting, it is greater than the other. Correct. Non-inverting, it is greater than the other. So your output will switch to positive side, but it will be inverted. Why it will be inverted? Because input is given to the inverting terminal. So as your input goes in the negative direction, your output will go in the positive direction, but again it will be saturated. So this is a comparator. This circuit, it is a comparator. It is analog comparator. How it is comparing? It is comparing the two signals. It is comparing the two signals. So instead of 0 volts, you can place here 1 volt or 2 volt, any voltage. Right? That will be acting as reference voltage. Are you people following?
Yes, sir.
Yes, sir.
Okay. So this was about analog comparator, right? So next we should go with the digital comparator. Digital comparator, what it does, it is just like another comparator only. It will also compare the two things, but in digital we have bits 0 or 1, right? So 0 or 1, right? Which one is greater than the other? If that thing is done by the circuit, then it is called as comparator. It will compare the two bits. So for that, what we have to do, we have to write the truth table. So it is A, B. Say we are having two variables A and B, and we will have four combinations 0, 0, 0, 1, 1, 0, and 1, 1. Correct? Now we have to write the truth table. How will we write the truth table? A greater than B. Where A is greater than B? Here, no. Here, no. Here, yes. Here A is 1, B is 0. Correct? So here A is greater than B. Rest other positions we have to write 0. Why? Because A is not greater than B. Correct? Then A less than B. Where is A less than B? Here. So here we will write 1. Rest other parts we will write 0. One more condition we have to take. Why? Because there is equality also, right? So we'll write for A equal to B also. Where is A equal to B? 0, 0, the first one, and 1, 1, the last one, and other two will be 0. Getting?
Yes, sir.
This is how we have written the truth table of comparator. Now using the K-map, you can just solve for the truth table and derive the equations for all the three. Which are the three? Say A greater than B. Correct? So A greater than B. How to write it? A is 0, A is 1, B is 0, B is 1. Correct? So you look for this one, A greater than B column. Where is it? Here. So 0, 0, 1, 0. We will fill the details 0, 0, 1, 0. Right? Now you group the elements. There is only one thing. There is only one here. So you write the equation for A greater than B. What is the equation? It will be A into B bar. Getting? Are you following?
Yes, sir.
Yes, sir.
A less than B. What will be the equation? Do you really need the K-map or directly you can write it?
Direct.
How? How did we write for this one? A greater than B. A greater than B is 1, right? It is true here, right? And what that condition is? That condition is A is 0 and B is, sorry, A is 1 and B is 0. A is 1 and B is 0. That thing itself we are writing here. A is 1, B is 0. Similarly, A less than B. Where is that? Here. So what will be the equation? A bar into B. A bar into B. Right. Next, A equals to B. Can anyone tell me what will be the equation for this? What will be the equation for this? If you get the doubt, you just go with the K-map. Okay. No need to think much. So you can go with the K-map. If you are not getting the things directly, this is the best way to solve the things. So A equals to B. Where we have? Here we have 1. Here we have 0. Again we have 0. Here we have 1. So write the equation now. So for this one, we will be writing A bar B bar. Correct? A bar B bar plus, here we will be writing AB. What is this? Any gate? Can you recollect any gate from this equation? Which gate is this? A bar B bar plus AB? Yes?
XNOR.
It's not.
Exactly. It is XNOR gate. So you can write the equations for, or you can draw the logic diagram now. So A, correct. So this is A. and this will be A bar, and say this is B, and this will be B bar, right? So now you take A, you take the A and you take B bar. B bar means it will be here, right? And just AND it. If you simply AND it, you will get the output A greater than B. Are you following?
Yes, sir.
Similarly, you can draw for the other things. So this was about digital comparator, right? So now let us come back to your circuit, right? So that circuit, whatever we get, that will be implemented on the digital trainer kit. But here it is being done virtually. Connections are already done, and let us check the result, right? So I'm just powering on, and next, yeah, both the switches A and B are 0 0. Yes, both are 0 0. Here also 0, here also 0. That means A equals to B should be high, that we are seeing here. Correct? So that you can in the truth table. Next, change it. A is 1, B is 0. A is greater than B. It is high. So here we are adding it. Next, change it. Both are 1 1. So again the third one. The last condition is happening. Means A equal to B. Right? Then you'll go with A0, B1. So I'm adding it. So all 4 cases are being added. Right? So we have similarly 2-bit comparator also. How to design 2-bit comparator? In the same way we can design 2-bit comparator, right? So how we will do it? Instead of this truth table, what you will write? Yes, what you will write instead of this truth table? Here, how many bits we needed? It is 1 bit, right? 1-bit comparator. If you require 2-bit comparator, then what we will do? You have to include 2 bits of A1 and A0, and 2 bits of B, that is B1 and B0. Correct? Yes or no? So you just write the combination 0 0 0 0. Right? Now check. All the zeros means A equals to B will be high. A equals to B will be high. Then you go with the other combination. Say 1 0 0 1. Right? Actually, you have to write down all the 16 combinations. But for example, I have taken this. So 1 0 0 1, which is greater than which one? A is greater than B here. So here you will write A greater than B. Here you will write 1. Here it will be 0. Here also it will be 0. Right? Then you take the next case 0 0 0 1. Here B is greater than A. So here B will be greater than A. That means A is less than B. Right? So you can develop the truth table accordingly. Understanding?
Yes, sir.
Yes, sir.
Yes, sir.
So what I wish you people to do is just write down. See, I received some comments over yesterday's homework, or you can say assignment. So those who are having the laptops or those who are having the PCs, please go with one experiment. Okay, yesterday I had said you 3 experiments, right? Just execute one experiment. Any of these. Okay, those who are having the laptops or those who are having the PCs, please execute any one of them. And how to execute? You have to add this, right? You have to just see, hardly it will take 2 to 3 minutes. You have to simply power on, change the combination, add it to truth table, and simply go with the print. This is the homework for those who are having the PCs or laptops. Only 2 to 3 minutes you have to spend. Click on the link, directly go with the playing with these buttons, add it here, print it. then save it, right? Say for example, I'll save it. I'll save it as a simulator, say on the desktop. I have saved it, right? Now it has been saved like a PDF. On the desktop, it is like a PDF. I'll just open it and show it to you. This form of PDF, you people have to mail me. See, you are seeing the results also in the truth table. Okay, so this is the homework for all those who are having the PCs. Okay, and those who are not having the PCs, you please design the 2-bit comparator on paper. Okay, no need to go with any PC or all. Right, on paper you just write the truth table. I have given you the clues. Right, write the truth table, write the K map, then write the equation and write the circuit. Understood? First, truth table. Second, K map. Third, equation. Fourth, logic diagram. So all these 4 you just write down on a paper. I think it will be completed within 1 paper, only a single sheet, and it will take just 5 minutes. Is it okay?
Yes, sir.
So this
Yes,
will
sir.
be, this will be evaluated for 5 marks for your lab, because you people are not doing any lab, because you are staying at home, right? And you are unable to come here. Even we understand. So this is just one homework for you people, and you have to send this. See, those who are doing on paper, those who are designing it, right, on paper, they have to scan it, write your name, USN, roll number, division on right top corner, right, and scan the paper and just mail it to me. I'll just send my email ID in the WhatsApp group. So some of you, those who don't have the PC, can go with this, and those who have the PC can just execute the virtual lab experiments. Is it okay?
Yes, sir.
Yes,
So the deadline will keep so today is the 16th. So the deadline will keep it before 21st. On or before 21st, that is Monday. So I'm giving you 1, 2, 3, 4, 5 days. So within 5 days, you can spend 5 minutes either in the hard copy that is on the paper, or in the simulation tool that is in the virtual environment.
Wonderful.
Is it okay?
Yes, sir.
Yes.
So here we'll be seeing the output for 2-bit comparator now, right? So this is the circuit. The connection is already done. We'll power on the circuit, and then we will look with the different combinations, right? So here we have all zeros. So already A equals to B is high, and these two are low. Let me change it. Let me make A as
So not audible.
You are muted, sir.
So what I was trying to tell you was all the input combinations you can try with, and you can verify the results. You know the theoretical results, whether that theoretical results is being reflected in the truth table. That is the question, right? So you can verify with the all the input combinations. Understood? You understood how to proceed with the virtual labs?
Sure.
Any questions, any doubts you have on this? Yes? Any questions if you have? So here we have for decoder, right? So this is 2 to 4 decoder. 2 to 4 decoder. When inputs A and B are 0, 0, here you are getting Q0 is high, right? When I make it 0, 1, that time Q2 is high. That means B is the MSB here, right? For 1, 1, Q4 is high. So again, sorry, you can add it. Whatever you are doing, you can simply add it, right? What is the use of resistor here? Can anyone tell? What is the use of resistor? 330 ohms. Yes? Why should we use resistor, or we need not use resistor? Can we skip resistor here?
No.
We can't skip resistor. Why so?
Affects LED.
Yeah, very good. LED, it may get damaged. Why it may get damaged? If large current flows through it, then it may get damaged. So this resistor is limiting the current. Why only we are choosing 330 ohms? Can we go with the different resistors? Yes. Can we go with the variety range of resistors? Say, can I use 10 kilo ohms here? Or can I use here just 10 ohms?
No, sir.
Why so? On what basis do we select the resistors? On what basis do we select the resistor? Is there any formula for that? Is there any concept behind it? You people know it or don't know it? Shall I explain, or you people know it? Yes?
Explain, sir.
Explain.
Explain, sir.
Okay. So basically, say I am giving 10 volts. Okay, I am giving 10 volts. I want to find out the resistor, which resistor I have to use. Okay, which resistor I have to use. So for that, say this is LED, right? So for that, what we have to do? Very simple. It is very, very simple. It is just Ohm's law. It is just Ohm's law, right? So what Ohm's law says? V equals to I into R.
R.
Correct. Now your LED should glow. It should not glow very, very dim such that it is not visible to us, and it should not try to glow in such a way that it will never glow in future. That means it should not damage itself, right? So these two scenarios we have to handle it carefully. So for that, current rating of LED will be given. That means what is the optimum current, what is the suitable current for the LED, means what current can flow into the LED so that the LED will not get damaged and it will give the proper result to us. Okay, so that current will be given in the data sheet. Data sheet means what? It is the summary of that LED, or what is the maximum voltage that LED can handle, what is the maximum current that LED can handle. All the data will be given in the data sheet regarding LED. Who will give it? Manufacturer, right? The person who has manufactured that LED, that person will give the details about that LED. Okay, so generally it is seen that maximum LEDs, they require optimum current of say 10 milliamperes to 20 milliamperes. This is the range of current which LED suits, well, right? Again, I am not saying that all LEDs will require this current. No. Okay, it depends from LED to LEDs, but generally we see that it is 10 to 20 milliamperes. Say in this data sheet of this LED, the current, optimum current, it is given as 20 milliamperes. Okay, so we have to look into it. We have to see that the current which is flowing through the circuit, it should not exceed 20 milliamperes. So for that, we have to find out the resistor. Very simple. What is voltage we are giving? 10 volts. Correct. What is the current which should not be exceeded? 20 milliamperes. Correct. Just solve it. Just solve it. 10 by 20. 10 by 20 is 0.5. Milli will come up. It will become kilo. Correct. So it is 500 ohms. Got? Understood?
Yes, sir.
It is very simple. There is no need to think much over this. So 500 is a resistance which we can use. So don't use the resistor which is lesser than 500. You can go with 600. If you use 600, this current may become a bit lesser. Say it may become 16 milliamperes. No harm in that. Okay, no harm in allowing the current up to 16 milliamperes. No harm. But if this current increases to say 100 milliamperes or 200 milliamperes, when that will happen? When I use the resistor 50 ohms. If I am reducing it by 10 times, this will be increased by 10 times, right? So if I am going with that, then there is a chance that this LED may not glow in future. Is it clear?
Yes.
Yes, sir.
Okay. So generally we see the resistors, they are current limiting factors used for current limiting. And also one more thing, what voltage will be dropped across this resistor? This thing we did not discuss only. What voltage will be dropped across this resistor? Again, Ohm's law, very simple. V equals to I into R, right? What current we are allowing it? Say I am using say I am using 400, right? No, not 400. Let me take the resistance, say 480. Okay, 480 ohms. If I'm using 480 ohms, right, then what will be the voltage drop across this resistor? I into R, very simple. What is current? What is current? Yes, say 20 milliamperes. Okay, into what is R? 480. So how much it will give? It will give us 9.6 volts. Correct. So voltage across this resistor will be 9.6 volts. That means what? Whatever 10 volts I'm giving, that is not directly connected to LED. Okay. Say I may give 100 volts also here. If I'm giving 100 volts here, then I have to look for a resistor which is capable of giving the required amount of current as well as voltage to the LED. Okay. So if you again go into detail of that, right, then basically you have to see that LED also has some resistance R, which may be lesser, okay, which may be negligible. Why negligible? Because LED, whenever it is forward biased, then only it will conduct the current. Then only it will be turned on. And we know LED is basically light emitting diode. Basically, it is diode only. Correct. So this is LED. Right. So whenever the diode is forward biased, whenever the LED is forward biased, then only it will conduct. And whenever the diode is forward biased, then its resistance will be negligible in terms of few ohms. Say maybe 100 ohms or 50 ohms. Okay, even maybe lesser than that also, depends on LED. Correct. But that consideration also comes here. No problem with that. But I just gave you the overview. Okay, so this will be the voltage drop across the resistor. And what voltage drop is across this LED? Remaining voltage 10 minus 9.6, say 0.4 volts. That will be voltage drop across LED. Understood?
Yes.
Okay. So I'll not take further more circuits on this virtual lab. We are just concluding the virtual lab session here, right?